Hi everybody, it's Mrs. Smith again. So we're back at it, still going in chapter 10 with thermochemistry. This video is all about Hess's law. So a good chunk of this chapter is focused on determining the change in enthalpy. So it's just different approaches to find delta H. So we talked about that in the last video with calorimetry. Remember, we're not really focused so much on the calculations, just kind of understanding what's going on inside the calorimeter. And there are three other ways that we're going to look to determine enthalpy changes. So we've got Hess's law, that's the focus of this video. Then we'll discuss enthalpies of formation, or delta HF. And we're also going to use bond dissociation energies. So lots of different ways to determine delta H. This video is going to focus all about Hess's law. All right, so remember that delta H, change in enthalpy, is a state function. So that means it only depends on the initial and the final enthalpy values, not on the pathway. So remember the image of a mountain. You can either take the long, arduous trek up the mountain and hike it, or you can take the ski lift. You're still going to get from the bottom of the mountain to the top of the mountain, so that's all we care about. So Hess's law states that if a chemical equation can be expressed as the sum of a series of reaction steps, the delta H of reaction, or the enthalpy change of the reaction, for the overall equation is simply the sum of the enthalpy changes for the individual steps. So that is a mouthful, right? But all it's saying is we can go from reactants to products. If we have two steps, our enthalpy change is simply the change of the first step plus the change of the second step. That's all it is. So I kind of liken this to, it's not really a great analogy, but kind of like Sudoku, but for chemistry. So it's pretty interesting. I think they're kind of fun, but again, I'm kind of a nerd, so I don't know if that's a good approximation here. So we see here an overall reaction of taking diatomic hydrogen gas with diatomic nitrogen gas and producing ammonia gas. All right, and our job is to figure out what the delta H of this reaction is. And we see that we can take these two reactions, all right, and sum them up to get to our final reaction. All right, so essentially we look here, we've got step one has this enthalpy change, right? It requires energy, it's got a positive delta H value. Step two is exothermic. It's got a negative enthalpy change, so it releases energy to the surroundings. So overall, we've just got this little energy release here. All right, so we've got to figure out how to take these two reactions and sum them up to get our total reaction. So essentially, we're going to work to add together these two steps to try to equal this overall reaction. All right, so a couple of rules we're going to hit in more detail on the next slide. But essentially, you want to make sure that what's on the reactant side in your overall reaction is on the reactant side in your steps reactions, and what's on the product side is on the product side. Anything that appears in the product and the reactants here can be canceled out. So those sorts of things are going to drop out to kind of give away to a net reaction. And if you've got things that are the same, that are on both sides, or excuse me, on the same side of the arrow, they can come together and be added together. So essentially, I like to think of this overall reaction as our goal reaction. So our goal is to find three diatomic hydrogens on the reactant side. So if we look, we see we have two in step one, and we have one in step two. So these guys can add together to be our three equivalents of hydrogen. Our next step, we have N2, so diatomic nitrogen. We see we have this guy here. So we can see him here, right? So we have our 1 N2, so that's all we need. For our products, I need 2 NH3s, which I see here. So we can simply just add up these reactions. I also notice that I have N2H4 on the reactant and the product side. So those guys are going to go away. All right, so those will cancel out, and summed together, we have our total overall reaction, right? So this is our goal here. So in order to find the delta H of the reaction, we can simply add together delta H1 plus delta H2 to give our delta H of the reaction. All right, so we just take 95.4 kilojoules plus negative 187.6 kilojoules. And we add them together to get our delta H of the reaction. So this reaction has a delta H of negative 92.2 kilojoules. So again, this is an exothermic reaction because the delta H is negative. It releases heat to the surroundings. All right, so let's officially write down some rules for these guys. All right, so again, Hess's law states that the overall enthalpy change for a reaction is equal to the sum of the enthalpy changes for the individual steps in the reaction. So to calculate delta H from our individual steps, we have to make sure that the reactants must appear on the left-hand side, or on the reactant side. The products must appear on the right-hand side, or the products side. All intermediate products must appear as both products and reactants and cancel. So that means they have to be in the same number, right? So if you have two, chlorines on one side, they can cancel with two chlorines on the other side. So sometimes in that first example, it worked out perfectly, but we all know in this class, not everything works out perfectly. So sometimes, you might need a compound to be in the product side, but it's actually on the reactant side in your step reactions. So what you can do there is actually just flip the reaction, and what was on the left goes on the right, what was on the right goes on the left. So if you need to write the reaction in the reverse direction, you have to flip the sign of the delta H. All right, so that means if it was positive, it would be the negative. If it was negative, it would then be positive. The number stays the same, right? But the sign changes. Sometimes you have to have them in a different number. So say you need, 2 sodium chlorides, but you only have 1 in your step reactions. So you can also multiply a reaction through by a coefficient, and you have to multiply everybody through reactants and products, even if you don't need them in number specifically. But its delta H must also be multiplied by that coefficient. So again, it's a lot of rules, but once you start doing the problems, I'm sure you'll get the hang of it. And these are actually, again, kind of fun. All right, so let's try a problem together. So here we've got our 2 step reactions. We've got carbon and carbon monoxide being combusted to produce carbon dioxide. We want to use these 2 step reactions to calculate the combustion of elemental carbon, so C, to carbon monoxide. So each of these step reactions have their respective delta H values, so we're going to use these to work together to get to our goal reaction. All right, so we have our goal reaction here in purple. Our job is to find this delta H of reaction. Then I have my 2 step reactions in black with their respective delta H values. So I'm going to call them delta H1 and 2 so we're not confused. Okay, so I like to deal with one reaction at a time. So I'm going to start with reaction 1, and then I'll talk about reaction 2. So before I start to do anything, I like to see what, essentially what I need from reaction 1. So I see that I have carbon in reaction 1, and I have oxygen and oxygen in reaction 1. Now, you should also notice I have oxygen in reaction 2, so the oxygen's not the main point of concern here. I'm really worried about the carbon in this case. So I'm going to write out my solid carbon plus my gaseous oxygen reacts to make CO2. Now, if you'll notice, I have 1 carbon here and 2 carbons in my goal reaction. So what I have to do is multiply this whole reaction by 2. All right, so that's going to be 2 solid carbons plus 2 diatomic oxygens gives me 2 carbon dioxides. I left off my gas here. All right, so that's going to take my delta H1, and I'm going to multiply it by 2. All right, because whatever you do to the to the reaction, you have to do to the delta H. So I have my two carbons. I'm going to highlight him so I don't forget. Okay, so I've got some oxygens. I've got a little bit more than I need, but we're not going to worry so much about that right now. The next step is to look at reaction number 2, which has 2 carbon monoxides as a gas, plus we've got 1 diatomic oxygen, and it produces 2 equivalents of carbon dioxide. So what do I see here that's similar to my goal reaction? So here I have carbon monoxide. I have that in my goal reaction, but I should notice that, okay, it's on the reactant side here, but it's on the product side here. So that can't do. So what I have to do is flip this reaction. All right. So what's on the left side goes to the right. What's on the right side goes to the left. So I have 2 CO2s that are gases, and that breaks down into carbon monoxide, got 2 of those, and 2 oxygen gases. So for my delta H2, all right, if I flip the reaction, I flip the sign on my delta H. So I'm going to put a little negative here to remind me to flip my sign. Okay, so now let's look and see what we have. So I have my 2 carbon monoxides, got my 2 carbon monoxides. Maybe those should be a different color. 2 carbon monoxides, 2 carbon monoxides. Highlight him so I don't forget. All right, so now let's look at my oxygens. Okay, I have 2 oxygens on this side and 1 oxygen on this side. So I can cancel one of those oxygens. Essentially, if they're on either side of the arrow, they can subtract from one another. So this guy goes away, and this guy goes down to just 1 oxygen. Okay. So now I have 1 oxygen left over on my reactant side, which is what I need. If we look again for what else we have here, I see that in my step reactions, I have 2 CO2s on this side, and I have 2 CO2s on that side. So they both subtract from one another. It gets me down to 0 CO2s. So now I see that I have everybody represented appropriately for my goal reaction. Everything else drops out. And that's the dream here for these guys. So to calculate your delta H of your reaction, you take your delta H1, and I multiplied that by 2. And I'm going to add to that negative, so the opposite sign of delta H2. So that ends up being 2 times negative 394 kilojoules plus negative 566 kilojoules. Negative. So that ends up being positive, right? So the sign just gets flipped. So I end up with 2 times negative 394 kilojoules plus 566 kilojoules, because again, we flip the sign here, to get my total delta H of reaction of negative 222 kilojoules. All right, so now I want you to try one. So here we have the step reaction of 2H2 plus O2 gives you 2 waters with this delta H of reaction. I want to know what is the delta H of reaction if we have 1 water decomposing to form 1 H2 and half of an oxygen. Okay, so see what you can do. You just got 1 goal, 1 step reaction. See what you can do to change this guy. And don't forget, every time you change this guy, if you flip him or multiply him or do whatever, you also have to do it to the delta H. So try it on your own, see how you feel, and then I'll talk through it with you. All right, so hit pause, and I'll meet back up with you in a few seconds. Alrighty, so let's talk through this guy together, shall we? So, again, look at your step reaction, see what you have, see where it needs to be. So you should notice that where we need water to be is on the reactant side, and in our step reaction, we've got it in the product side. So the first thing we have to do is to flip our reaction. So we have 2 H2 gases on the reactant side, breaking down into 2 H2 gases plus an O2. All right, so the first thing we have to do is flip the sign on the delta H. Okay, so it becomes positive 484 kilojoules. Remember, same number, opposite sign. Okay, so now everything's where it needs to be, but my numbers are off, right? So I have 2 water molecules or moles of water here, but I only need 1. So last time we were multiplying stuff, but you can also divide. So now I'm going to divide everybody by 2. So I go from 2 moles of water to just 1 mole of water. I go from 2 moles of hydrogen gas to just 1 mole of hydrogen gas. And I go from 1 mole of water to just a half mole of water. Now, I recognize that, we always tell you never to put fractions when you're balancing equations, which is still very true. But here, we'll see this again when we talk about enthalpies of formation. Sometimes you're going to see fractions, but when you balance them, never ever use a fraction, unless it's an enthalpy of formation or something. But we'll talk about that in a minute. Okay, so let us see. So I've got 1 water. I've got 1 water, I've got 1 hydrogen, I've got 1 hydrogen, I've got half of an oxygen, I've got half of an oxygen. Okay, so everything's as it should be, so I just have to pay attention to my delta H. So I flip the sign in my first step. For my second step, I have to divide it by 2. So here, our delta H of the reaction is 242 kilojoules, and that's positive. So my answer here is letter A. So again, not super challenging, just take some time, take some practice. You're just moving some stuff around, multiplying, dividing, flipping things. Nothing too tricky, just write everything out, cross things out, highlight, circle, whatever you need to do. So hopefully this isn't that bad. But again, work through practice problems. That's the only way you're going to get good at it. And reach out if you have questions. All right. Thanks, guys. Have a good day.